change. We should be able to find the average rate of change of a function over an interval, which is what we're going to focus on today. Find a rate of change at a point using small intervals containing the point. We'll do that today. Describe relationships between the rate of change and the behavior of the function we'll get to next class. Okay? Is everybody good? All right. So first up, we've talked about rate of change. We've talked about the slope of the line being interpreted as rate of change. The rate of change function is defined as the rate at which the output quantity changes with respect to the input quantity. If the graph of function is not a straight line, we're going to use the terminology of average rate of change between any 2 points. So pretty much we're just finding the slope between 2 points given an interval. So if I'm finding the average rate of change between this x value, x of 1, and this x value of x of 2, we're just finding the slope of those points is really what we're doing if we're asked to find average rate of change between an interval. Okay? All right, so let's go and do that. So we need to find the average rate of change of this cubic function, x to the third minus 4x, over the interval, and for some reason it disappeared on me. What is it, 1 to 3? From 1 to 3. So what I'm going to do is I'm going to figure out what my output is. So if I have x is equal to 1, what is f of 1? What would that be? 1 minus 4, so negative 3. If x is equal to 3, what is f of 3? 3 cubed is 27 minus 12, so that's 15. So here are my x's, here are my y's. Let's go ahead and find the slope. Instead of using m for slope, since we're not finding slope, we're finding average rate of change. We're going to do AROC, AROC for average rate of change, is equal to, and I'm going to write this out just so you have it for your notes, f of 3, I'm going to do the larger first, minus f of 1 all over 3 minus 1. Well, we just found f of 3. That was 15. We said f of 1 was negative 3. Divided by 3 minus 1, which is 2. So we're doing 18 divided by 2, which gets us 9. So my average rate of change on that function, again, since it's cubic, we're going to have 2 terms in it, n minus 1. We'll have 2 terms in there, but from 1 to 3, the average rate of all those instantaneous rates of change is 9. Okay, so it's like we turned off the lights, Fred ended up in place B, and we could say, well, on average, we think his rate of change was 9. Got it? Okay, example 2. Here we have a table from the University of Michigan Center for Sustainable Systems showing us solid waste mass in tons, right? So garbage from 1960 all the way up to 2018. Part A, we want to find the average rate of change in trash between 1985 and 1990. So we're right here in this chunk. We'll have years be represented by our X. Total waste will be our Y. Can we find the slope of those values? I hope so. So our average rate of change is going to be equal to, I'll do the larger first, so 208.3 minus 166.3 divided by 1990 minus 1985. Is everybody okay with me just throwing an answer out there? 8.4 million tons is the average rate of change in that 5-year stretch. For part B, we're asking whether the rate of trash ever declined in this 58-year period. Does anybody see a decline anywhere? Looks like, right here, 2005 to 2010, we have a decline happening. So let's figure out how much it declined by. So let's find the average rate of change or the slope within that interval. So if we do 251.1 minus 253.7 all over 2010 minus 2005. When we do that math out, we get negative 0.52 million tons. So I wonder what they did in those 5 years to cause less waste. I don't know. That's when you guys were born, right? 2005 to 2010? Maybe that's when disposable diapers became a thing. Who knows? Okay, questions with those 2 questions? Easy enough? Okay. Example 3. After surgery, you are given a pain reliever. The level of medication will decrease slowly over time. We're going to let C of T represent the medicine's concentration in your body. Write an expression for the rate of change of the medicine's concentration level over the period of time. So all we're doing is just writing an expression. And we're doing it from 15 minutes to 90 minutes. So our average rate of change is going to be equal to our concentration output at 90 minutes, so C of 90, minus our concentration output at 15 minutes, so C of 15, divided by 90 minus 15. So the only thing I can really do here is just simplify that denominator. So average rate of change is equal to C of 90 minus C of 15 divided by 75. So we don't have the function to input the 90 and the 15 to get actual output values. Okay.
Do you want to switch the 90 and 15 because the change is going to be negative, or is that not?
It doesn't matter. It doesn't matter. Because that would make sense if it's negative, because with time it should be decreasing, right? So you would get a negative no matter in the numerator or the denominator. So if you had C of 15 minus C of 90, you would end up with negative 75 in the denominator. Okay, and the last one. Here we have a graph representing a car's travel over a 2-hour stretch. Notice my x-axis is in minutes, from 0 minutes to 120. My y-axis is in distance, jumping by tens. We want to know what the average rate the car travels in that 2 miles. So that means we're going from beginning to end. So we can either just calculate our rise, oops, I went too far, our rise over our run, or we can use our slope formula. So average rate of change is equal to, let's do large number first. So our distance evaluated at 120 minutes minus our distance evaluated at 0 minutes divided by 120 minutes minus 0 minutes. Our distance at 120 looks like it's over there at 100. Our distance at 0 is 0. So 120 divided by 12, what is that, 5, 6? Okay, so here we got to do some analysis on our units. So we have 5 miles per 6 minutes. But whenever we're talking about speed, we always talk about miles per hour. So what do I need to multiply 5 miles per 6 minutes by to get to hours? 60, right? So 5 miles per 6 minutes, multiply it by 60 minutes, gets me to 1 hour. So that cancels out my minutes. And I think that ends up getting us 50 miles per hour. So the average speed that the car traveled in the 2 hours time was 50 miles. It wasn't 50 miles per hour, 50 miles per hour. Wasn't that the whole entire time? Here it's a little slower, here it's faster, and so forth, right? But in average, from beginning to end, we're at 50. So now we're going to do it between the interval from 30 to 60. Well, again, I could just look at the graph and go from 30 to 60 and count my rise over my run to find the average. Or we can do it out by hand. So my average rate of change is equal to the distance with my 60 minutes minus my distance with the 30 minutes, all over 60 minus 30, which distance at 60 was 40, distance at 30 is 20, all over 30 gets us 2/3. And again, that's miles per minute. I got tiny fingers there. So multiplying that by 60, so 2/3 times 60 will cancel out our minutes and leave us with an hour. And that gets us to 40 miles per hour. So we averaged 40 miles per hour from 30 minutes to 60 minutes. Okay. And then the last three. Is everybody good? Okay, so C, when is the car traveling the fastest? So when is it going the fastest? It looks like we're going the fastest between 70 and 90. Looks the steepest on our graph. Is everybody in agreement there? So between 70 and 90, between 70 and 90 minutes, how fast is it going? Our average rate of change is equal to, what are we at 90? 90, we're at 80. I'm just going to go right to it. So 80 minus at 70, we're at 50. Over 90 minus 70, which simplifies out to 3/2. Multiplying that by 60 gets us 90 miles per hour. Whoa, we're speeding there. Slope between 90 and 120. So again, we're just doing the same thing. Average rate of change, distance at 120 minus distance at 90, divided by 120 minus 90. Where are we at 120? We said we were at 100. 90, it looks like we're at 80. 120 minus 90 is 30. So 2/3. Multiply by 60 again to get it to miles per hour. We did that in the first one, didn't we? Isn't that 40 miles per hour? And then for the last one, 45 minutes. Look where 45 falls on your x-axis on that graph. I'll go back to it. So 45 doesn't happen at a really nice spot. It's like right here. So maybe it's traveled like 32, I don't know. But that dot falls on the line between what two endpoints? 40 and 60. So if I can find the rate of change between that, it would be the same rate of change as that linear chunk that's between those two. So let's go ahead and find the rate of change between 40 and 60. So we're going to do an average rate of change between 60, so the distance at 60 minus the distance at 40, divided by 60 minus 40. And that is 40 minus 30, all over 20, which is 1/2. 1/2 times 60 means it would be 30 miles per hour would be the speed at 45 minutes. Questions? I know we went through it pretty quickly, but I feel like it's about the same thing over and over again. Yes, what do you got? The last one?
Yeah.
So we were looking to see what the average or the speed is at 45. So since 45 lands on this linear chunk, the rate of change is going to be the same no matter if it's here, 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 here. So if I can just find the slope between those two endpoints, that will be the rate of change at any point on that line. Okay? All right, so